Hey, this is John Willis. I've got my good friend Mark Burgess. Hey, Mark, say hi to everybody.
Hey everybody. Hey
Yeah,
John.
yeah. We decided to actually start a podcast series. We're going to call it for now. We'll call it "In Search of Certainty." And Mark and I have been pretty good friends for a number of years now. I mean, I think maybe going back 5 years at least when we first met. And in fact, I might even tell the story of how we met. That might be fun. But we've had great conversations. Mark has been an incredible mentor to me to understand this concept of kind of certainty and uncertainty, or non-determinism versus determinism. And so I, we at DevOps Days Italy a few years back. I had the great opportunity to get to hang with Mark on an extra day where we just walked around Rome for the day. And it was just the greatest conversation because we talk about the industry. He'd kind of educate me on physics. We talk about kind of in search of, this concept of certainty in IT. And it was just an amazing, and we've had great conversations since then. And the other day we were talking about something pretty intense, and I was thinking, you know what, we should do a podcast. Right, Mark? What do you think?
It was probably pretty disrespectful of us to be walking around Italy, right? We should have been looking at all the great sites because around every corner there's like a new one. Seriously, another one,
Well, that was
another monument, another fountain, another building, and now we were just talking about IT and all of this cool stuff. But
that, that was pretty
I
funny.
remember that conversation very fondly.
Yeah, it was kind of funny. You're right. We were just kind of we had no agenda on where to go, like no map, nothing. And literally we'd look up and say, "Is that the Coliseum?" "Yeah, hey, that's the Coliseum. That's awesome." And then we talk about the Coliseum a little bit. Then we just walk randomly. I think by the end of the day, we walked all day, and then near the end, we just tried to get on like, okay, now we're going to come back to reality. We are indeed lost. We don't have maps. Let's just figure out the subway system. So yeah, that was great. I did want to start one other thing I hadn't thought about, which is how we first met. I was certainly aware of your work, but I had just come off working for Chef, and I remember giving a presentation at Scale, and I did the kind of the deadly sin of describing configuration management, which is so this was probably 2011, maybe 2012. So I got a big old screen. It's a big old room. And right when my slide says, these are the configuration management tools that you need to be aware of, which listed just Chef and Puppet. Right as that screen, I don't know if you remember this, Mark, you walk in through the back door and you look up at the screen, and I went, "Oh, hi, Mark." And we hadn't, I don't think we had met, but I obviously knew who you are. And I'm like, "Oh, and CF Engine." And then you came up to me after and said, "John, why can you help me understand why everybody lists, only two and not three?" And I had left Chef, and in my respect for you, I was like, you know what? I'm going to take this on as a project. And I spent really the next year or so. So it had to be 2011 because I spoke on Promise Theory in 2012, I believe, at Scale. So I literally, I wanted to figure out what the answer to that question was. I don't think I've ever really answered the why, but I did get a better understanding of how you thought, and the ideas that you have brought to our industry, which are tremendous. So it was kind of cool.
Well, thanks so much for saying so. I appreciate that.
All right.
And I also appreciate our friendship over the years.
So. Oh, it's been great. It's been awesome. Yeah. Anyway, I want to get to the meat of this, but the one thing that I think this podcast will show is Mark's amazing ability to take extremely complicated concepts and break them down to levels of people who don't have engineering degrees or physics degrees. So with that, let's go ahead and start. We talked about your recent blog article called Artificial Reasoning in Non-Intelligent Systems. If we can get to that near the end, but one of the things that you've constantly said, and you say this in your book, In Search of Certainty, that the thing that gets us in trouble, or the thing we don't understand, and it in general, kind of in life and everything we do and how we measure and think about things, is scale. And so I'd love you to walk me through this idea of how scale gets us in trouble, and if you can tie that back into how that gets in trouble in just general IT. And, you know,
Right.
So,
Well, I think it's interesting because, as many people know, my background was in physics rather than in IT. And so I learned about scaling in physics before I ever came to the IT world. And it never occurred to me not to think about scaling as I would think about it in any other system. But in IT, scaling has it's come to take on a very particular meaning, which is what we're concerned with in IT is delivering services, pumping out services on the internet, typically web services at scale. And when we talk about scale, we mean sort of amplifying the output. So it's like making an amplifier. We'd start out with one computer in the olden days, and it would be like a single PC. And input would come in, on a socket, and then you'd fire up the reverse socket, and the output would go back. And eventually that becomes a bottleneck. So you're trying to expand the output of this thing to more customers. So you're trying to build a kind of an amplifier for your service. And so when we talk about scale in IT, we're thinking about how many machines can we throw at the problem of amplifying the output of our particular service in order to cope with the demand. And that's not quite what scaling means in physics, because that ability to amplify something is kind of neither here nor there. And how big something is, people don't really care about that. But say the ratio of the size of something coming in to the size of something going out, that is something that people think about in physics. And the dimensions of an object, let's say you take something and ask yourself, is this a functional device? So I have a glass of water in my hand, and you can say, is this a functional glass? Well, it's about twice as tall as it is wide, and it's about the same size as my hand. So the ratio of my hand to the glass is about 1. And so it seems like that would be a good match. These things would be able to interact. But suppose we change the scale now in a physics sense and make the glass either 100 times smaller or 100 times bigger. Suddenly it doesn't interface very well with my hand, because the ratio of my hand to the glass is like 100. Either 100th or 100, it doesn't really matter. The fact that it isn't about 1 means that these things don't interact very easily with one another. And so in the physics world or in the science world, when you talk about scaling, you're often looking at how well things behave or how systems perform as functions of these ratios of scales. And scale simply means anything that you can measure. So it may mean the size, it may mean the number of atoms or the number of computers or something like this, but it may be the height or the length of time it takes to start up your computer, or the length of time it takes me to talk, answer your question, or whatever it happens to be. Whatever you can measure, it's a scale. And when sort of the ratio of these scales changes considerably, things typically change in your system as well. So it stops performing in the old way and it goes over into some new way of performing. Sometimes that can be quite dramatic. Most people know about the idea of a phase transition, like when ice turns into water and water turns into steam, or vice versa. And these things are actually examples of phase transitions where there's a scale parameter which changes. And as this scale, this ratio of scales changes, typically based on the temperature versus the energy, these things are related, and then you take the ratio of two so-called dimensionless quantities, and as that approaches one and becomes smaller or greater than, something changes in the system, like changing from ice into water. It's not always quite that dramatic, but sometimes it really is. And so when I started thinking about scale in terms of IT and IT services, my first thought was, oh, I wonder what the dimensionless variables are for this. You know, how do we compare a small system to a large system? And actually, how can we be certain that as we grow this system, it doesn't change its functionality in a qualitative way, like turning from, you know, a solid to a liquid? How do we know that the data center doesn't vaporize or something like this? It's maybe a joke, but in some sense, you would expect something fundamental to change as something like that happens. And the scaling ideas that we have in IT turn out to be quite limited because of the way we build IT systems. You know, this goes back to Turing machines and von Neumann architecture. Basically, a computer is a queue, and we're squirting like a queue of work like toothpaste into the machine, and it's like a long, thin stream of work coming in, and we're trying to push it out at the other side. And we know it's a kind of a bottleneck. Everybody understands the concept of a bottleneck. But the question is, you know, as the amount of this stuff coming in gets bigger and bigger, how is this going to affect the scaling of the services? And if we think about it in terms of queues, we have quite a limited idea of understanding the scaling, because a queue is actually a very, very simple thing, and it's already an abstraction, an idealization. For a single computer, it's not a bad idealization, but I mean, we'll get into probably later why the concept of a queue itself doesn't scale all that well as we change the dimensions of inputs and outputs and so on. But in a queue, things are very simple. A queue basically has two states. There's lightly loaded, where everything's going pretty well, nobody's really queuing up, everything's just flowing through the system nicely. And then there's super overloaded catastrophe, nothing's working, the system's thrashing, everything grinds to a halt, like traffic on the 101, or, you know, think of any queue you can think of. And the turning point between those two states is very small, because a queue goes like a power law. And so that, you know, that flip over point from very small to functioning very well to functioning very poorly is very short fuse. So, you know, when that happens, our first thought is, you know, how can we throw more power into the queue? How can we make the queue go faster? And this has led to this idea that over the years, IT scales simply by throwing more computing power at the problem. And we'll come back to Moore's law, and, you know, the processor going faster, or adding more memory or more cache, or all of this kind of stuff. But this is basically what we think of in IT when we're trying to prevent the queue from blowing up. We're trying to increase the resources somehow for this single queue. And I think it's important to just see how that idea is slightly different from the idea of how relative capacities or dimensions or things you can measure bear up against one another, and whether or not that affects the qualitative nature of the system itself.
So let me squeeze in some dumb questions, or kind of high meta questions, to break it down. So this concept of that, you know, that maybe how we manage, what we do, the humans interact, everything, where from how we build code to how we build infrastructure, all that is kind of, in your analogy, the hand. And the infrastructure that get deployed is the kind of glass in the water. And at some point, the scale of the one, in this case, the kind of infrastructure, the implementation of all this stuff, has some type of turning point, like you're kind of turning to steam, if you will, water turning to steam, but the whole glass and like whatever glass does in physics when it gets expressed at a certain, I guess it melts, right? The glass melts, which would be, and the problem that we have, or the kind of initial idea that you're trying to express is, we need to understand that there is this, we are at some point, if we haven't already crossed it, or a company like Google and Facebook probably already have, but at some point, the mismatch of the hand and the all the things that make it up, and the glass and the water being the infrastructure itself, get incredibly mismatched. And if we don't recognize that, the pressure we apply, or the continual, or the inappropriate actions. Am I like summarizing that correctly, or?
Yeah, and I think you make the point that which I didn't quite make, which is that this congealing of a cue from some freely flowing, beautiful fluid of output to some treacly mess, whilst when the system starts thrashing, is almost like water turning to ice or something like that. It is almost like a phase transition in some sense as you cross this threshold behavior.
Yeah, cool. So, yeah, I mean, I think I still kind of want you to drive. I just wanted a checkpoint there, so I still want you to kind of drive down your kind of space, time, and scale, and where do we, So, all right. So we're possibly with certain IT systems, our kind of toolbox, if you will, might not be appropriate. I think you made an interesting quote in one of your articles in the book, in that, let's see if I can dig this up. I don't have that great of memory. Software systems do not obey the law of physics, even though they run on. No, that's not the one. I mean, I think the point you were making is we really need to understand, as we get into a world of what would be very small. So I'm thrashing here. What happened between kind of Newtonian physics and quantum physics was, some people understood that we made this phase transition, if you will, in understanding just physics. And some people recognized it, some people didn't. The people who recognized realized they had to kind of change their instrumentation of how they measure things. So I guess my crazy, wacky question, even we might not even make this public because I'll sound too stupid, but so my crazy question is, how do we capture? And I think you're already in the place where you're saying, hey, that transition by assumptive method is already there, so this is the way I'm going to start thinking about how I adapt to that phase transition.
Well, I think anybody who thinks like a physicist has got to ask the question. The first question you ask yourself when you look at a system is, what are its scales? And then, how many different dimensionless variables can I construct from this? And I go through this in my book in some detail. It's called the method of dimensional analysis, and it simply starts like that. You look at all of the measurements that you can take in the system, and you construct all of the ratios of things that can be relative to one another. And then you ask yourself the question, what can happen when these scales change? Is it just the shape? Does the key no longer fit into the lock? Or is it, if they scale in proportion, is it just getting qualitatively bigger? Is it somehow the same? This goes to the point of how in physical systems we often use that property to test things. So think of a wind tunnel, which is an example I used a few years ago, the making of a software wind tunnel. Because it's so expensive to build a real plane or a real car or something like this, we don't do that and try to fly the thing. We build a scale model of the plane and then test it in a wind tunnel to try to understand the aerodynamic flows. And if you simply make a smaller version of the plane from balsa wood or something and stick it in a wind tunnel and hit it with air speeds typical of a plane, you won't learn anything about what a real plane would do at that speed. It would just because the ratio of the size of the plane to the wind, through some conversion factors no longer matches.
There'd be some little kid crying, right?
Right.
Okay, sorry.
But what you can do is try to work out what the right wind speed should be for that size of plane after you've done that. And take a corresponding example in software, maybe in visual recognition, which is a popular thing these days, right? So, of course, everybody's trying to recognize cats, obviously, on the internet, because what else? And then ask yourself, when you see a cat, how do you know that this is like a regular cat close by? How do you know it's not a 2-story cat 2.5 miles away? Well, actually, if there's nothing to compare it to, you don't, right? You have no way of knowing. You're just, well, maybe we'll come back to that. But typically what we do is we compare the cat to whatever it's standing next to, and we say, okay, cat is standing next to a glass. We've already established that the glass is the size of my hand. The cat is about the size of my hand. It's not the size of a 2-story building. Whereas, if it was a Godzilla cat 2.5 miles away, standing against some tall building, you know what the building looks like, and you can compare the size of the cat to the building. If it's got its paw resting on the roof and it's a tower block, it's a pretty big cat. But then you could also say, well, how do I know that that's a building like 2.5 miles away? How do I know it's not a box close by? Well, actually, because the size of a window doesn't change very much relative to the size of a building, because windows have to be the size of a human being, because they're for letting the light in for us, or a door or something like this. So there are things that pin scales at a certain size. Now, the size of a door doesn't scale. When we double the size of a building, we don't increase the size of the door. We don't double the size of a door, because functionally, it's the ratio of the size of the door to the size of a person that matters, not the size of a door to the size of the building that matters. And so it's through these comparisons that we establish functional relationships. And this, I think, is the key in computing, because, of course, physics it doesn't care what the function of something is. It's all about objective measurement, right? But in IT, it's all about, what does this do? What's this going to do for me? What function is it going to perform? And so the first thing that we start out with in IT is that certain scales are pinned by the things that they need to interface with. And this is true, for example, even in a web service, the incoming traffic to a web service is pinned by the scale of a socket on a single machine. You can't really send an incoming, excuse me, you can't really send incoming traffic to 100 machines simultaneously. Actually, some sense you can, but it would be a dumb thing to do. But you can you can pin that doorway into the computer at that scale without restricting the scale of the outgoing door, which is maybe broadcasting the results of your input to a whole bunch of different people. So when people are watching Netflix or something, the output bandwidth is going to millions of people around the world, whereas the incoming connection from each individual person is going to a single spot point in a particular location. So this notion of scaling is subtly different in IT, because functionality pins scales to these particular interface relationships. Does that make some kind of sense?
Yeah, no, it does. It does. And I guess, so how do you, again, I guess I'll go back to, are we recognizing this kind of, large gap happening between kind of the interface, the scale, the interface on kind of input and output, and how that's affected?
I think, that's a great point. I don't think we do understand that very well, because we're stuck in this notion of a queue, and the queue is one-dimensional, and it has to go into a socket, it has to come out of a socket. So the only thing you think of if you think like that, the only thing that you think of is, how can I make the computer process things faster so I can squeeze more things in the input and output, in a shorter space of time. But actually, the Netflix example is a good example of how you can't simply squeeze the output through the machine faster, because you don't want to watch your video at twice speed, right? So if you double the number of consumers, you don't say, well, everybody had better watch it twice as fast so that I can handle the total number of users in the same amount of time. Actually, a colleague of mine at the university, when I was a graduate student, used to joke that he thought it was dumb when on the freeway they close a lane because there's a traffic jam, or there's an accident or something. They close a lane, and then the traffic goes slower. But his idea was, that's dumb. You should make the traffic drive twice as fast, because then they would all get through in the same amount of time, and you keep up the throughput in this way. So that's kind of a joke, but it does illustrate the point that just by doubling something naively to try to maintain the same flow, you don't necessarily, it's not necessarily going to go well for you. In the case of the cars, because they probably crash and burn.
Or white making people. Although I do certain presenters, I have to put on the 2x speed on YouTube, so that's kind of cool. That's been to be able to whip through a presentation where you just want to get to a certain point. I guess the thing is, so we're not there yet. We still have a lot to learn. We're trying to figure out, or you are doing a fantastic job of trying to help people understand how physics, how we're going to get to a scale of very small, if we're not already there, in what we do in IT, and how we have to think about, kind of space-time and semantics. And I guess so I'd heard a story, I won't attribute to anybody or any product, unless you want to add more, but I heard a story once that a large financial institution, they turned configuration management monitoring on at a certain a scale that really had never been done before for traditional like Chef, Puppet, CF Engine, whether it's 5 minutes, 8 minutes, but maybe down to, and I'm using literary license here, so, but they turned it down to maybe seconds or something like the really, really small. And what the output, and he did this for like a day or something like this, and the output was that it's so, like in your book you talk about, like if you have a wool sweater, and you try to figure out the knittings of the fibers of the band, you can't do it. But if you were to expand the sweater to be this gigantic sweater, I'm sorry. If you closed your eyes and you took a wool sweater and you tried to figure out the patterns and knittings with your fingers, you wouldn't be able to really do it because your fingers in scale to the knitting are so small. But if you made the sweater 20x or 30x, maybe 50x, right? You put your fingers, you can say, with your eyes closed, you can say, oh, I can see this stitch pattern, right? And so in this example, it sounded very similar in that they were able to see all these, what they thought were a well-managed kind of planned system, managed changes, at one scale, was like chaos at this really, really small scale, in terms of, unplanned changes, like millions, maybe even billions of unplanned changes that were basically not seen at the other scale. And I guess, so that's one question, but I think then, in your book, you talk about the Lorenz and the butterfly effect, right? So, I mean, I think there has to be something there, right? Like, in other words, like, do we, if we don't understand the scale of what we're dealing with, are there's all these things going on that we have uncertainty, if you will. And then I guess I'm going to throw in the kind of the hat trick here, and then goes back to how do you attack uncertainty? And I suspect it's through kind of probabilities and things like that. So that's
Wow, that's a huge bunch of questions. You may have to remind me about the butterfly thing at the end, but yeah, that's great because it's getting towards this idea of non-indeterminism,
Right.
which, by the way, physicists also learned by trying to scale machinery and during the Industrial Revolution. That really all came out of scaling steam engines in a sense. But let's go back to this financial monitoring scenario. I remember an episode like that. I think I wrote about it in my book, where a very specific software thing happened because we were monitoring or collecting stream of data into a monitoring system, which was going into a database. And the database, of course, because this is a regulated institution, has to have high availability. So it's got to be running all the time, and that means that the database needs to be replicated. So there's not only a stream of data coming into a database, but there's a stream of data going from one database to a couple of other replicas at the same time. And as probably most people in software know, while it's a fairly straightforward thing to do to parallelize incoming sockets and incoming traffic to some sort of collector, database replication is typically serialized because you're trying to preserve all kinds of transactional properties, whether for good or for better or for worse. And maybe it's not even an appropriate thing to do anymore for certain kinds of databases, but often the technologies we have are trying to serialize transactions in order to have ACID properties and so on. And what happened at this institution was that a software improvement in the collection actually made the data collection go faster into the database in such a way that the replication process couldn't keep up. So the replication process didn't scale when the time scale for data collection changed. The replication time scale didn't change. And so suddenly the queue got imbalanced and the whole thing ground to a halt. It started thrashing, data started building up, and the queue flipped from that nice fluid mode to this horrible congealed mess mode and backed up the whole system in very short space of time, much to the embarrassment of the software developers. But of course, the irony was that their software had actually improved, and it was that improvement which had caused the bad behavior of the queue. So that's my phone ringing in the background.
Yeah, I got it.
And this is, in a sense, this was what happened when people studied physics originally. They were trying to build these steam engines, and it's a bit like you start out with a boiler, creating some pressure, which is driving an engine, maybe turning the loom in a factory or something like this. And you manage to make your boiler work at twice the efficiency, but the pipes carrying the pressure to drive the motor aren't twice as big. So suddenly they become a bottleneck or a throttle on the performance of the whole system. Maybe they even blow up at some point. So actually, it was that problem that physics was trying to solve in the 1800s that led to the whole of thermodynamics, which led to statistical mechanics, which actually came out of this very interesting observation that in fluid flows, fluid is not like a queue. It's not like a digital process. Fluids get compressed, they have pressure, they have temperature, and they behave differently depending on a whole bunch of different variables, not just density. And in certain regimes, they actually become chaotic. The behavior becomes chaotic. And that means that it becomes very hard to predict exactly how they're going to behave because they enter into this regime where everything becomes very nonlinear. A very small change in one part of the system can lead to a very big change somewhere else that you weren't expecting. And that turns out to be, the beginning of a whole new science almost of understanding this business of indeterminism, non-determinism in systems. Prior to that, of course, the world had been very Newtonian, and Leibniz and Newton and these guys had all of these beautifully decoupled systems, the Earth and the Moon and the planets. They were looking at these, very geometrical, perfect. They even tried to model them as perfect polygons and polyhedra and so on. But thermodynamics kind of messed up. It made physics kind of messy. And the best way we were able to try to unravel it was by looking at the complexity and trying to embrace the complexity of what was going on instead of trying to search for the internal simplicity, which was the Newtonian approach.
So I think there's a hook, right? In that, the guys like Boltzmann and all those guys, right? Like they got to a point where they couldn't really, through kind of deterministic method, or their deterministic methods of measuring things were just broke. Didn't make sense. So they had to go to a kind of a probability model. So we've had this discussion. So the transition of kind of steam engines to kind of thermodynamics, and that we're in an industry right now that is in kind of every sense of the word stuck in a deterministic think pattern. And even though we there's a lot of thought leaders will say complicated, complex, and chaotic, the Cynefin model, whatever. Right. At the end of the day, it seems that as an industry, we still can't get out of the box of unconsciously thinking that we can deterministically force our steam engines to go faster. So the flip,
right.
Yeah. So the flip, yeah. So I was just going to say the flip needs to be at what point or what tools or what is the driver to move us from jargon about complex systems or chaotic system or chaos to actually doing it, if you will.
Right. I mean, first of all, I think that what you say is absolutely right, that people not only don't appreciate this lack of determinism, but they actually don't want to, because it's a huge inconvenience to be working in systems that are not deterministic, right? Our whole nature of interacting with the world is kind of based on determinism, because that's what we think we experience on
we're humans.
A day-to-day basis.
We're humans. We created these things. Of course,
Yeah,
we should be able
right.
to hit buttons to make them work the way we want. Yeah.
Right. I mean, it's very much this notion that we are in control,
right.
And we like to be in control. And this was very interesting reading. The book that came out, about the SRE book that came out about Google recently, described Google's rise to meteoric scale, of course, and in a very interesting way. Described how they were forced to face the problems of scale, but in some sense chose not to, or not to present those complexities or indeterministic aspects to developers, because developers found it very hard to have to deal with that when writing software. So instead, the operations teams built systems to try to preserve determinism, or the illusion of determinism, for developers at any cost, by basically throwing brute force at the problem and trying to replicate databases using these Paxos, Raft replication algorithms to give the impression that scale actually didn't matter as far as writing the software was concerned, which of course is a functional decision. It's a functional criterion. So it's, again, because the scale is now pinned, the size of an internet cat has to match the size of a Google server or something. That scale is now pinned. But when the backend has to deliver this cat to 100 homes, instead of the software itself having to adapt to that, they would carry the burden of that, of making that work without the developer having to think too much about it, which I think was an interesting.
It's actually
approach.
so. It's funny. I read that book recently, and I was reading the forward, and I was just reading. I'm like, this is cool. This is pretty insightful. And I get to the bottom. It's Mark Burgess. I'm like, holy shit! I know that guy.
Yeah, I was honored to be able to write the intro.
That was awesome. But so now. So I guess this is quantum physics in implementation of a podcast, because I don't know what direction we're going to go next. But that's interesting. The kind of Google SRE, it's almost a paradox, right? Like, in other words, they kind of created an implementation of a wind tunnel, but by kind of abstracting. Determinism by, again, making the developers feel like they're in a deterministic model, when the true implementation is, I guess I would, yeah.
I think what I find potentially dangerous about that story is that, Google were able to do this because they had incredible resources. They had computing resources like no other company had, right? They had huge data centers,
right. Yep.
Incredible talents, incredible people to be able to manage these systems, to be able to rewrite software. And this is not something that an ordinary company or an ordinary development team or operations team would simply be able to do or reproduce necessarily beyond that kind of environment. Of course, now that we're kind of moving into the cloud, and we have Amazon and Google and various others managing this for us, some of those considerations are being taken on or being taken away from developers in a similar kind of way, but not necessarily all of them, because to maintain that illusion, it's really a systemic thing. Like we were talking about, it's not just one ratio that has to stay the same, it's all the ratios throughout the system, from the network to the server, the CPU, the memory speed, any kind of scale or time scale or size of a container that you can think of. Whenever any one of those things changes relative to one another, that potentially is thrown up in the air.
Well, go ahead.
So, I mean, just to finish this story, and last year I was invited to talk at a very interesting conference in New York, where I met Jeffrey West from the Santa Fe Institute, who turns out to have a background very similar to mine, actually, in physics. But he's turned his attention, along with Louis Betancourt and people from the Santa Fe Institute, to studying the scaling of another kind of functional system, which I believe is very similar to servers or IT systems, and that is cities. I've said many times before that a city is basically a big operating system. And it has many of the same kinds of issues as computers. It has transportation networks, it has functional processing, it has relationships, it has networks, and so on and so on. But what was, I think, fascinating from the work that they did at Santa Fe was they were able to study data about the scaling properties, physics scaling properties of cities, from quite small cities to very, very large cities across the world, and really observe generic laws for how these functional systems scaled in quite extraordinarily predictable ways. And as I was listening to this talk, I thought, yes, I know how to do this. This is right up my alley. First of all, they're talking my language, and I know that using promise theory, we can build up a story to explain how this comes about and how this really scales from small to large. And although it seems today like we are hitting big scale in IT systems, we haven't really approached the scales of the largest cities in terms of how we utilize networks. And by that I mean, we'll get there pretty soon, but by that I mean the penetration of networks on the internet is still pretty much a one-dimensional kind of, it's like we've got one gigantic tunnel across the Atlantic, everyone goes through the same tunnel, and then it fans out to a couple of data centers, but it's a long axon, basically. But in a city, the networks of roads are very much two-dimensional things. They're not one-dimensional. And they penetrate space densely. Much like, in pictures when you see an expanded lung or an MRI scan of the body, the capillary system, the way veins and capillaries penetrate into an organism, they fill that space in a very different way to the way our networks, our IT networks, fill space. And it turns out that when the guys at the Santa Fe Institute discovered the scaling laws of a city, double the size of a city, how many supermarkets are there relative to a small city? Does it double? Does it halve? What happens? Asking these kinds of questions, they came up with these very precise laws, and they found out that the only way they could explain the scaling properties was to understand the dimensionality of the space, not as a cube. It turns out that queuing theory was not able to reproduce their answers. So there's a first indication that the models that we're using in IT will actually fall flat on their face in a very large functional system. And we're only just around the corner from, the Internet of Things or highly complex memory systems like AI systems, where the penetration into storage systems, memory systems, resources, even huge data centers will become very much two-dimensional, three-dimensional. And these models we have of queuing, simple queuing in one-dimensional systems, just won't cut it anymore in terms of the scaling properties. I mean, I would be very surprised if the big guys like Google and Facebook and so on haven't seen this already to some extent. They may not have understood what it is that they're seeing. Actually, I did hear from IBM that they had started to see some of this.
We're seeing this all the time with like kind of what we think are black swan outages, right? Like, our human interpretation of a black swan is it never, ever, ever happens. Oh shit, it happened yesterday. But the truth of the matter is, one of these days, I think I want to get Dr. Woods or Cook or Decker on his podcast, because those guys talk about, like Decker talks about precursors, and I always get this wrong, but Woods talks, I'm just going to call it near misses, that so with a bunch of stuff I want to kind of decompile here. One is, I think what you're saying is, even though Google and Facebook seem like incredible scale, maybe they're not as complicated as we think, right? Like, in other words, like in your book, In Search of Certainty, you asked me to remind me about the butterfly effect, right? You talked about how measuring and modeling orbits is easier than weather patterns. Yeah. Right. And it seems to me that maybe, IT, and your analogy in the book is the orbits, and, cities are closer to weather patterns. But
well, in a way, it's this. It goes back to this issue of stability. Again, think of the phase transition, the queuing transition, flipping from calm and peaceful to crazy, chaotic thrashing. It's like when you're trying to predict the weather, because the weather is non-linear, chaos, non-stable system. Basically, those sort of high-pressure days when nothing's happening, it's very easy to predict the weather because nothing's happening. So that pretty much good prediction is that nothing's going to happen. But on those days when everything is happening and nothing is stable, it's really hard to predict the weather because it's all happening and you really have no idea what's going on. So it's almost a self-fulfilling prophecy. And I think the first message that comes out of this from a practical perspective is that we need to be building systems for stability first, not for scale first. Mm-hmm. The scale is meaningless. Unless you can construct a stable system, it won't be functional. And it has to be stable at the scale of the things that it's interacting with.
Well, it's got to be, so to kind of paraphrase or kind of summarize, like, back to, you said, that the Santa Fe Institute folk, that they went ahead and created kind of figured out by modeling the generic laws of small cities that were consistent between cities, and you call it the scaling laws of cities, but we need a scaling laws of IT. And even if we're not there yet, we are going there, and we already see examples of it in stability, right? Where we have these black swans. So in other words, we need to attack this problem by thinking about like what are the kind of the laws of IT that apply to a small system, medium system, large system. Is it? Yeah.
Yeah, and this has been the subject of my research actually in the last couple of years. I realized that, I've been writing about this for years and years at different levels. First, it was a book I wrote for Wiley called Analytical System Administration, which was a first attempt. It was almost like rediscovering cybernetics, but for IT.
Is that what you talked about? We're going to run out of time, but autonomic systems, and is that the book?
That's where it kind of started, yeah.
Yeah.
But then I realized something was missing from that, and that was the intent, the purpose of the system was kind of missing, and that aspect is what physics doesn't get, right? So you deliberately try not to talk about the purpose or the meaning or the interpretation of anything in physics because it's trying to be very generic and impartial, deliberately impartial. But actually, in a functional system, that works against you. You want to know what the function of it is, the purpose of it is, because you're trying to preserve that through all of the other changes that are going on. So engineering has had more of a tradition of understanding scaling in functional systems. And I was trying to write down or discover some of these laws by applying a promise theory alongside this scaling theory. And I've been trying to write down some of these things, and of course, this is, in some senses, it is easier because IT systems are, to some extent, more linearizable than things like the weather. They're more controllable than things like the weather, but at the same time, there are other complications like the discreteness of things, and the many different purposes to which we turn things, the idea of promises that we're trying to keep, and the fact that it's an interaction between human and machine. It's not just you can write maybe a law about how a steam engine works, but if you try to add in the operator of the steam engine, suddenly that law may not make sense anymore. So trying to model people in the system at the same time, which goes towards Sidney Dekker's work and so on, then it becomes much harder. But I do believe that it is possible to capture some aspects of those systems. I don't believe it's hopeless.
Well,
I have seen some complexity people complain, not complain, but it's the word, come out and say that, because complexity, blah, 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 it's impossible to predict, blah, blah, blah. I don't believe that. I think one of the things that physics is very good at is extracting the essences of things and knowing the boundaries within which certain behaviors will be stable or not stable.
Well, isn't that, the Santa Fe people in the study of cities, right? Like, people are an integral part of that, right? I think, is it that is it kind of human hubris in that, that we think that we have to, the human is kind of decoupled from the system, and therefore when we think about how do we deal with complex and chaotic, as opposed to maybe, it seems to me that the people who are studying cities, the Santa Fe people, the Jeffrey West gentleman you talked about, they're clearly not decoupling the humans from the study of the city, right? The humans are certainly part of it. So again, I think, isn't that where we need to go, right?
Right. So actually, this is a perfect subject for the continuation of this, for the next exciting episode, if you like. How do we get to that point where we understand the coupling between humans and machines? And in the case of cities, what they discover is, in fact, they they're looking at a regime which is at such a large scale that actually it doesn't matter what the nature of those things in the city is, because the relative scales are so large that they actually completely decouple from the nature of the things that make them up, which is why you can compare Beijing to Stratford-on-Avon or New York to Honolulu or something like this, whatever it is. You can compare these things because actually the underlying pieces don't matter. In the same way that it doesn't matter which atoms make up your sofa that you're sitting on, it's just sort of comfy or it's hard, but the particular things going on inside, what it's made of, are not that relevant at that scale. So we have something to understand here, which is how, first of all, different interventions by outside forces, different interactions, whether by human or by machine or by dinosaur killing asteroid or gigantic cat, Godzilla cat, whatever the intervention is, how that interacts with the stable behavior of the system, and how, when you scale that system, how does that stability become affected by it? And at some point, you would like to be in a situation where actually it doesn't really matter because it's so stable that it just keeps going no matter what you throw at it.
Yeah, no, I think that's a good place to end, is that that one of the things we probably haven't done yet or don't have a full understanding is how to be able to kind of turn the knob on scale to find the kind of persistent properties of IT. What is a 3 system? What is a 100,000 system? What is a million node system? And what are the constants there? Again, sort of like what the cities are doing. A lot of what you talk about in the first couple of chapters in Search of Certainty are what the people in physics had to do, right?
Exactly.
Well, I think that's a great place to end. I think we're just about at an hour. We'll definitely we'll figure out what the next. We've got a queue of things. If you want to send us emails, I'm botchicaloop@gmail.com. Mark, what's your best email?
My email is quite a long one, so it's mark.burgess.oslo.mb@gmail.com. Don't ask the origins of that. It's a long story.
So if you guys are listening and you want to kind of fire some questions or what you think we should expand on, go ahead and do that. We might actually have the next podcast recorded before this gets, but hopefully not. One of the things we were thinking about doing is have Mark really break down all the confusion, the positives and the negatives of CAP theorem in an upcoming episode. So anyway, it's been a blast. I kind of figured it would be. I was a little scared at first. I thought maybe I was not going to be able to keep up with you, but looks like I held my ground. So sound good? Thanks, Mark.
Thanks, John.